Okay, so we're looking at the vector separation as applied to Coulomb's law. And we're going to do a little bit of practice here on this today, and then you'll have some other additional practice problems with the homework. So we'll start, as I normally do, sort of scaffolding it by looking at different possible scenarios. And so I've got some problems that we're going to take a look at, and we'll use those as examples as we're going. Now, before I get into a problem, I want to come back over here to our textbook. And on Blackboard, we have our diagram here, which I'm going to copy and paste into our document here. So these are diagrams that came from the textbook from Chapter 2. And so I will put that here. And then I will also cut and paste our equation that we're going to be working with in terms of the Coulomb's law equation. Just as a reminder, so some of the things that we had covered already. And again, if you go back and you look at the notes from the 20th, we went through and looked at how the new version compares to the old version, and we had equations and things like that in here that we're going to be working with. So again, what we have to do here is we have to start with sort of one equation at a time, and we will use our little q as being some source charge, which is at a fixed location, and then our q is our field point, which could potentially move to different places. This is also referred to as our test charge. And this is the one that we're finding the force on it. So this equation here finds the force on big Q due to little q. And so we have to sit here and think about what this separation is. And so that separation is our main focus of stuff today. And again, that's our separation, and I have a hard time with my handwriting issues writing that out, but that's the cursive R there. And the magnitude of it is just the distance, but we also can express it as a vector separation, and we can express it as a unit vector. So before we get into the equations, I'm just going to point out to you here that this vector starts at the source charge and goes toward that field point. Okay? So when we look at the diagram here in terms of the way that arrow is shown, and I'm going to put this up on the board because I've just realized that I'm doing this on my computer and don't have anything showing on the board. So I'm going to pause my video for just a moment here. Oh, no, I don't have pause, so okay, it's just going to have some extra stuff in there we don't need. Okay. I was wondering why you were just looking at your notes, not looking up at the board, and then I'm like, oh, wait, that's because it's not up there. Okay, so again, the source charge is over here, and that's my little q, and this is my big Q, my fixed point in space. And so the separation vector starts from here and points out to there. Okay? And then I'm going to go ahead and grab from our equation sheet. Make this bigger before I grab it. These equations, so we can start talking about those. And then the textbook points out that the field point is the one at x, y, z, and the source point is at the x prime, y prime, z prime. Okay, so if I were to think about this, what I've got here is this one up here is my field point, so that's the x, y, z. And this is the x prime, y prime, z prime. And I'm starting here and going there. Now, these equations are similar to our displacement equations in the sense of I've got sort of an initial and a final. But we don't call this a displacement because displacement is where the same object moves from one place to another. And so we have an initial position and a final position. And so even though this equation looks very much like I've got my r minus my r prime vectors, it's not delta r, because delta r would be a displacement, and that's a single object moving from one position to another. So conceptually, displacement is that, but this is not delta r, it's our separation r. So displacement is a single object that moves. Separation is two objects at different locations. So that's why we've got a new terminology here between displacement and separation vectors. Mathematically, though, it works the same way. If I think about when I used to have things like delta x was equal to an x final minus x initial, now I've got the x part of the separation being my field point minus my source point. And if I look at my diagram again, it's because I'm starting the arrow here and going to there, so my field point is like my final position, and my source point is like my initial position. So hopefully you can see the parallels in the mathematics there. And then we've got the same sort of thing here if we wanted to look at the y component of the separation and the z component of the separation. Now, if all you need to find is the magnitude of the force, then we don't need the direction and we just need the separation. And it doesn't really matter which one we call little q and big Q, because once you square those terms, add them up and take the square root, it's equivalent whether we've got those things reversed from each other. So we have the same magnitude of the separation. The separation distance is the same between little q, big Q, and from big Q to little q. But the direction of the vector is definitely going to be different. So again, this is going over and talking about the equations. So now we want to go ahead, and I'm going to put this in the same video just for some continuity. I could have separated this into 2 videos. Let's actually do an example. And I'm going to make up some numbers. Okay? So let's say we have a charge, and this charge happens to be 2 microcoulombs. And it happens to be at a position, and since I've used little q, this means this one is what I'm calling the source. And so I express its position as, and just for simplicity, I'm going to use integers here to make life easier for us. I'm going to say it's at 3 I hat plus 2 j hat minus 4 z hat. And no, that should be k hat. So it's a 3D vector with 3D components. So this means that x prime is equal to 3, y prime is equal to 2, and z prime is equal to negative 4. Make sense so far? Okay, now I'm going to have another charge, capital Q, and it's going to be 3 microcoulombs, and it's at a position, and because it's big Q, this means this is the field point or the test charge. And I'm going to give it some different positions here. I'm going to make it 1 I hat plus 3 j hat plus 0 k hat. Which means that x is equal to 1, y is equal to 3, and z is equal to 0. Okay? Now I made these numbers up, so eventually it might get a little messy in terms of actually calculating everything, in terms of it not being, when I take square roots and squares of things, they may or may not actually end up integers, but that's okay. We're working with this right now. You could imagine, and we'll talk a little bit more in one of our lectures next week about sort of visualizing 3D space. But we've got our vectors here. Now I'm going to take my equation again, and so rather than recopying it from the textbook, I'm just going to come up here and grab this again and paste this down here. And we're going to plug some things in here. Now for our separation vector, and I just want to remind you guys here that the textbooks use boldface as being a vector. Because I can't do boldface very well, I put the arrow over the top to say this is a vector. It's got components in each direction. So if I was going to do this, my x is 1, my x prime was 3. Also notice that they use x hat, y hat, and z hat. I'm so used to doing I, j, and k hat. Those are the same thing. They mean the same thing. A unit vector in the x direction, a unit vector in the y direction, a unit vector in the z direction. So I'll just do that with my I hat, otherwise I confuse myself. 3 minus 2. And then it's going to be 0 minus negative 4. So we can simplify this, right? So what am I going to have? Negative 2 I hat.
Plus 1 j hat. Plus 4 k hat.
Okay, because I had a negative minus a negative sort of thing. Okay? So that is my separation vector. And ideally, I should have put units in here. So this would have really had, say, units of meters or centimeters or micrometers or whatever the heck it is. And so this also has units of meters. Because in physics, we have units on everything. Now, if I just need my separation, I'm basically doing the 3D Pythagorean theorem. So I'm taking minus 2 squared plus 1 squared plus 4 squared. And then I take the square root, excuse me, of that entire thing. Which I can do part of these numbers in my head. 2 squared is 4, 1 squared is 1, and 4 squared is going to be 16. And so this is going to be the square root of 21. Now I can plug that in the calculator and get it as a decimal number, but for right now I'm going to keep it as the square root of 21. And that's the square root of 21 meters, or the square root of 21 meters squared, because the meters would have been in there squared inside it, but when we take the square root of meters squared, it gives us meters. So this meters is outside of the square root in terms of our final answer. And then my r hat. Okay, so the r hat part here is going to have basically, this is my r vector divided by the magnitude of r, if you look at the way it breaks down. So you can do it all at once, but it's kind of messy when you do that. Or we can go through and say, for this particular case, r hat is going to be minus 2 over the square root of 21, I hat, plus 1 over the square root of 21, j hat, plus 4 over the square root of 21, k hat. And again, you could plug these in and get decimal versions of the numbers. Right now, I'm not going to, but we'll see how in some problems, depending on the geometry of things, things simplify out. Okay? So this allows us to find our separation distance and our separation unit vector. Now again, I'm going to stick in the same video for right now, but we could think of this as breaking down into another problem. I'm going to go ahead and now grab this and add another page onto my notes. And I'm going to copy some of my stuff over here now, because what I need is my two charges. Wait a second, where did that go? I put this in the wrong place, I think. I'll have to change these page orders later. My two charges and then I will grab what I found for my R value and my R hat value. And we can put these things in now. So what I've got here in terms of my answer, before I simplify it all out, is that this force vector is equal to 1 over 4 pi epsilon naught, 2 microcoulombs, 3 microcoulombs, over the square root of 21 meters squared, and then this unit vector, the minus 2 over the square root of 21 I hat plus 1 over the square root of 21 j hat plus 4 over the square root of 21 k hat. And yeah, I got really tiny as I was writing that in there. Okay, so again, just to summarize, I plugged in the value for little q, the value for big Q, the value for the separation distance, and what I got for the unit vector into those locations in the equation. Obviously, I can plug in also here my value for epsilon naught, which is 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. I put my meter in the wrong place there. And then you can actually get a number for this, which I'm not going to go through and do that as a stage right now. But that would give you a force, and it's easy to see then that I'm going to have a component of the force in the I hat direction, a component of the force in the j hat direction, and a component of the force in the k hat direction. I'm also going to point out something to you here in terms of this equation. Because r hat is r vector divided by r, we also sometimes end up writing this equation as the force vector. Let me actually do that in a different color here. I've got the 1 over 4 pi epsilon naught q r cubed, and then my r vector. Writing that one out, uses my vector form of the separation. And then I end up having a r cubed on the bottom. So r hat was equal to r vector over the magnitude of r. And so that adds an extra r on the bottom, taking it from r squared to r cubed. But then this is not a unit vector anymore. It's a full separation vector. So there will be some times where it might be easier to use this.
Let's have that with that.
Now, I fully expect that you guys are going to have to take time outside of class and look at this again and maybe plug it in. And I may go ahead and do the calculation myself, and then you guys can do the calculation yourself and compare it to my calculation that I'll add into the notes later, because I'm going to rearrange the order of the pages anyway, since I put this in sort of weird. Okay? Now, as a reminder, this was the force on big Q due to little q. If I wanted to find the force on little q due to big Q, I can do that. The easiest way is to recognize that if this is the force on big Q, the force on little q is going to be equal and opposite of the force on big Q. We know that from Newton's third law in terms of the force pairs. In terms of the mathematics of it, if I go back and I look at those r vectors, I'm basically switching which one is r and r prime, which means I switched the order in here. So instead of it being 1 minus 3, it's 3 minus 1. Instead of it being 3 minus 2, it's 2 minus 3. Instead of 0 minus minus 4, it's minus 4 minus 0, which means it's exactly the opposite vector. Graphically, if I was looking at the force on the other one, it's like I'm looking at, well, let me do this separately. It's now as if I've got big Q here and little q here, but now my vector separation is going to go from big Q towards little q. And I didn't get it exactly on the arrow, but you guys get the idea. So it's the same separation distance, but in the opposite direction. Now, these positions do not necessarily correspond with the positions I gave you, because I gave you an x, y, and z. but conceptually, if those were my points, that's why the two of them are in opposite directions for each other. Okay? So you can calculate the Coulomb force on one charge due to the other charge, and then you automatically have its pair as you're going through. Okay? So this gives us how we are working with these equations in terms of the math with these vectors given nice numbers. Now I'm going to stop this video here.